All right, question number 10 from the homework. It says the diagram below, not drawn to scale, shows a circle, center O. SGH is a tangent to the circle. Angle FOG is 180 degrees, and angle DGS is 65 degrees. Calculate, given reasons for each step of your answer, the measure of I, angle OGF. So angle OGF, this is the angle they're asking you to find. Here's how I would go about finding this angle. OG is a radius of the circle, and OF is also another radius. So that would make triangle FOG an isosceles triangle. For the isosceles triangle, the equal sides meet at the apex. Opposite from the apex is the base. And the two base angles of an isosceles triangle are equal. So I would say that angle, I would say, give me a second. I would say that theta plus 118 degrees is equal to 180 degrees. And these are the interior angles of an isosceles triangle. They are the interior angles. So that is my reasoning for saying that these three angles are the interior angles of an isosceles triangle. 2 theta would be equal to 180 minus 118. So 2 theta is equal to, this will be 62 degrees. Divide both sides by 2. So theta, which is angle OGF, is equal to 31 degrees. The angle is 31 degrees. The next angle we're asked to find is angle DEF. Angle DEF, that's this angle here. Now, as it is now, there's no circuit theorem that's going to allow you to find that answer directly. You're going to have to find something else before you can find it. But here's what I know. I know that DEFG is a cyclic quadrilateral. DEFG is a cyclic quadrilateral, and that opposite angles of a cyclic quadrilateral would be equal. So if I know, opposite angles of a cyclic quadrilateral would be supplementary. So this angle here and this angle here, this entire angle here, those two angles would add up to 180. The only thing is that I don't know this piece of that angle. I'm going to call it alpha. Now here's where OG is a radius at the point of contact. SGH is a tangent. G is where the tangent touches the circle. G is called the point of contact. And OG would be a radius at the point of contact. And the radius at the point of contact is at right angles to the tangent. That means that this angle here is 90 degrees. So I would say to the examiner, so this is for I would say that alpha is equal to 90 minus 65, which would be equal to 25 degrees. And then the reason for that is the radius at point of contact is at right angles to tangent. So you notice how I write the thing in shorthand? You don't have to write it like that, you can spell it out. Radius at point of contact is at right angles to tangent. So these two angles are now 31, sorry. So this is 31, and this is 25. So the entire angle there, angle FGD, or I could go straight for the answer. That's angle DEF, yeah, DEF, DEF would be equal to 180 minus 25 plus 31. And the reason for that is that they're opposite angles of a cyclic quadrilateral. They're opposite angles of a cyclic quadrilateral. So this will become 180 minus 56. This would be 124 degrees. Angle DEF is 124 degrees. This angle here is 124 degrees. How did I arrive at this conclusion? I have to find this entire angle here, which is 25 plus 31, making it 56. So the 56 degrees and the angle up here are opposite angles of a cyclic quadrilateral, and opposite angles of a cyclic quadrilateral are supplementary. They add up to 180 degrees. So that is our final answer and the end of the question. And the DEF is equal to 124 degrees.